Okay, we're on the applications of oscillation, maximum, minimum, and zeros second page. Here we're looking at acceleration, and we're trying to find first where the acceleration is zero. The acceleration is always the slope of the velocity graph. So the velocity graph is has a zero slope. Here and here and here, all of these high and low points. That's where the slope is zero, so that's where the acceleration is zero. If I look at where that is on the position graph, that's the points where the velocity is at a maximum at the equilibrium points there. So what's happening here is that the reason the spring accelerates is because the spring is either stretched or compressed, or the pendulum is away from its equilibrium position. But at that moment, when it's at its equilibrium position, it's not stretched or compressed, or the pendulum's not away from the equilibrium, so there's no force pulling it back, so it's not going to accelerate. So it's going really fast, but it's not accelerating when it goes to the equilibrium position. It accelerated all the way towards that position, which is why it's moving fast when it gets there. And then all the way on the other side of that position, the acceleration changes direction, and it's going to slow down the motion. The acceleration is a maximum places where the velocity graph's slope is biggest. So that's a place like this. That's a negative acceleration that's big. And this is a place where there's a positive acceleration that's big. So it's all these 0 points of the velocity, which are the minimum and maximum position. So at the amplitudes, that's where the acceleration is at its maximum. Sorry, I wrote 0. I didn't mean that. This is where the acceleration is positive. This is where acceleration is negative. Alright, so the zeros of the acceleration are where it's moving the fastest, where it's at the equilibrium point. And the maxima and minima of acceleration are when the spring is most stretched, which is when the velocity is 0. So when it's stopped and it's turning around, that's when its acceleration is the biggest. And when it's just moving very fast through the equilibrium point, there's no acceleration at all. Okay, now we want to calculate that maximum value of acceleration. So I'm just going to pick one of these. They should all be the same if these are all perfectly symmetrical, if these are all the same. I'm going to draw a tangent line. Okay, on my computer I don't have a ruler, but you would actually use one. So I'm drawing a tangent line to the graph there. I'll pick this point because it's right on the 6-second mark. And I'm going to try to pick, say, this point because it looks like it's right at 5.5 seconds. So my acceleration is the slope of that line, which is the change in velocity divided by the change in time. That's my rise over run. So the final velocity looks like it's about 0.4 meters per second. The initial velocity was negative 0.2 meters per second, and the time that it took for that to happen was a half a second. So our delta V is 0.6 meters per second and a half a second. So that's going to be 1.2 meters per second is our maximum acceleration. It's that positive, and then over here on the other side is that. It's the negative of that, and just sort of oscillates between those two values.